Hello, students of 11 General Maths, and welcome to exercise 3J, similar solids. Now, similar solids is just an extension of the concepts you've learnt about with similarity of shapes, especially triangles, in previous grades as well as in year 11. Now, before we move on, let's just remind ourselves that even though similarity has a common use definition in the English language, meaning that two things are alike, but not specifying how they're alike, we actually have a specific and rigorous definition of similarity in mathematics, and that definition is the one down here. It says that if two shapes or objects are similar, all of the corresponding angles are exactly equal to each other. So when the shapes are at the same orientation, then the bottom left angle has to be the same as the bottom left angle in both shapes, and the top angle and the bottom right angle or whatever. All shapes have to, all angles that correspond to each other must be exactly equal. The other fact that we need to be true is that all ratios of the corresponding dimensions must be the same. So that means if the base of one triangle is 2, the base of another triangle is 4, we've doubled the length to get from one to the other. That means the height has to change by that same factor for the triangles to be similar. So if the bases are both go from 2 to 4, therefore doubling, and the height of the first one is 3, the height of the second one has to be 6 because it must double as well. So those are our definitions for similarity. And so far, we've only looked at similarity in 2 dimensions. Here's just an example of similar shapes in 2 dimensions, just to remind ourselves. We know that these are similar because all of the angles are equal, because all of the angles are 90 degrees, because these are rectangles, okay? One of them was marked in there for us to show us that the rest of them are 90 degrees as well. The other thing is here, the height of my rectangle is 3 centimeters, and it moves up to 6 centimeters. So we've got a scale factor of k equals 2, as in we're doubling from one to the other. Now, my widths of my rectangles go from 4 to 8. And yes, that is doubling as well, k equals 2. So they're in the same ratio. The heights and the widths are in the same ratio for these rectangles. They both have a scale factor of k equals 2. So what that means is the angles are exactly equal and the sides are in the same ratio, so therefore the shapes are similar. So now let's look at what similarity looks like and what it means for us in 3 dimensions. So this is our first example. We've got two cuboids, cuboid A and cuboid B, and they are both rectangular prisms. Now, for our cuboids, we know that they are similar because they are the same shape. Both of them are cuboids, and the ratios of their corresponding dimensions are the same. So this 1 is tripled to make 3, this 3 is tripled to make 9, and this 2 is tripled to make 6. Now we've got cylinders, and we know they are similar because they're the same shape. They're both cylinders, and the ratios of the corresponding dimensions in these cylinders are the same. We start off with 2, and then it's scaled down to 1, so it's being halved. We start off with 6 for the height, and it's scaled down to 3, so it's also being halved. So we have the same ratio. Both dimensions are halved to get from one to the other. Now here we've got some cones, and they are similar as well because both of them are the same shape. And in fact, this needs to say cones, not cylinders. Both of them are the same shape, but also the second fact is true. The ratios of the corresponding dimensions are the same. So here we've got 20, and 20 divided by 4 is 5. And 6 divided by 4 is 1.5. So we could say the scale factor going from this triangle to this one is 0.25 because the dimensions are divided by 4 to go from one to the other, i.e. they're being multiplied by a quarter, or 0.25. We could also say that the scale factor going from cone B to cone A, if we wanted to go back the other way, is 4. K equals 4. Because 5 times 4 is 20, and 1.5 times 4 is 6. So we could express the scale factor going in either direction. Whichever we'd prefer to work with is fine. Both of them are correct. So those were some examples. Let's now have a look at what similarity does to the volumes of 3-dimensional shapes. We've had a little bit of a look at what they do for areas, but let's just remind ourselves. Essentially, if we have a scale factor of k, that's our linear scale factor. Then that means the area scale factor will be k squared. So we've already learnt about that. This is just a reminder. And now that's because we're working in square units, and then when we're working in cubic units, as you might expect, the volume scale factor is k cubed. Okay, so what that means is, for example, if k is equal to 2, k squared, the area scale factor, would be 2 squared equals 4. And k cubed, the volume scale factor, would be 2 cubed, which is equal to 8. So what that means, for example, is if I have a cube and I grow all of its linear dimensions by a factor of 2, so I double them all, its volume is actually multiplied by 8. So let's just see why that would be the case over here. We'll use the rectangular prisms from before. We'll see why that would be the case. So cuboid B, its volume would be length times width times height. Now we said before the scale factor going from cuboid B to cuboid A is 3 because 1 is tripled to make 3, 3 is tripled to make 9, etc. And 2 is tripled to make 6. So that means the volume of cuboid A, the way we could work out its volume is with 3 times the length because the length is tripled, times 3 times the width because the width was tripled, and 3 times the height because the height was tripled. So then if we factor out those 3's, we end up with 3 by 3 by 3 multiplied by length times width times height. So expressing that another way, what we have is 3 cubed times volume of cuboid B. So cuboid A's volume is 3 cubed times the volume of cuboid B, which is what we just discovered over here. That if we've got a linear scale factor, we cube it to get the volume scale factor. Alrighty, let's take a look at this in an example question. So this question says these two cones are similar. The ratio of their heights is 3/1. So that means this 9 is tripled to make 27. K equals 3. Now A says determine whether the smaller cone has been scaled up or down to give the larger cone. Now the height grew, so obviously it was scaled up. Okay, now B says what is the volume scale factor? So we know that the linear scale factor is K equals 3. Okay, and the working for that is just that K is equal to the image length over the object length, which in this case is 27/9, which is 3. Alrighty, so we know K is equal to 3. So what will K cubed be? So K cubed will be 3 cubed. And 3 cubed is 27. So the volume scale factor is 27. What that means is the volume of the larger prism, the larger cone will be 27 times larger than the volume of the smaller cone. So we tripled its dimensions, but that means its volume is now multiplied by 27. Now let's have a look at C. So C says the volume of the smaller cone is 120 centimeters. So V small equals 120 centimeters cubed. Okay, and we know that the volume of the large cone is equal to 27 multiplied by the volume of the small cone. Okay, because it's 27 times larger because of the volume scale factor. So that means the volume of the large cone will be 27 times 120 centimeters, the volume of the small cone. So using my calculator, that's 27 times 120 equals 3,240 centimeters cubed. So that's using scale factor for volumes and similarity in solids. Thank you, Year 11.